Okay, can you guys hear me? I should mention before we start that there was I got an email notification about Zoom that starting soon, you're gonna change the requirements for accessing Zoom lectures. I am not quite sure what changes this means for us. I do want to show you that when you go to the so try to see if I can get this to make sure that everybody who wants to watch this live can do it inside inside the Zoom announcements. There is a announcement that's called passcodes for lectures and office hours. So if you go in here, you can find the IDs and the passcodes. And I'm not sure how it's going to change on your end, but at least here you can find the numbers and the passcodes, and this should be enough to get you into these meetings. I'm not sure when the changes are to take place, but yeah. And the same thing for the TA session. There's a link here that will give you these passcodes that you might need. But just a heads up, I'm not sure why this change was made from the administration, but it's not something that I have. I don't have anything to do with it. Okay, so let's get back and talk about how to create the expectation of a more general random variable than these default simple. Some people call them elementary default simple random variables. If they only take on, in this case, one possible value down here, you're taking on m. M is finite, but m is a number in the natural. M is a natural number. So it takes on m different, possibly different values on each of these cells here, on each of these blocks. The random variable x will take on the value y. This is block number 1. It'll take on the value y1. And on block number 2, on A2, it'll take on the value y2. So these are the building blocks. And then how do we get the general case? Well, maybe before we do that, let me just recall. So a key difference to Riemann. So a key difference to the Riemann integral is sorry, I illustrated. So here I have my function, and let me just do it from 0 to 1, and let me do positive numbers again, just like we're doing for x. So if I do a Riemann integral of a function, so it runs from 0 to 1, the way that, and I'm just making it positive, so this will be my function. The way that we do a Riemann integral is you discretize, or you split the x-axis into bins. So here you will have, say, this will be x0, this will be x1, x2, and so on, and then you have it up to say xn. And so inside here you have some step of delta x. What you're going to be doing is you will approximate somehow with squares, and you will split the x-axis into these bins. So there will be x, you want to keep it over to the left, and then xn to xn plus 1, and they're equally sized often. So your difference, this is simply just delta x. And so you want to approximate the area underneath the graph by rectangles. And so you put in these rectangles, and so you compute these areas. Right, so you you want to look at the integral of f of x dx from 0 to 1. You're thinking about this as being some sort of a limit as delta x goes to 0 of these sums when you're summing over, what would it be if you do left endpoints? It will be f of x and then n times delta x, something like that. And the key thing is that we split the x-axis. So we can't, so because omega is abstract, we can't split it. We can't split it like we just split the interval 0 to 1. There is no way that we can just, if I have omega out here, this omega is not just a segment of the real line. It's much more general. So we cannot just split it like we just did. There's no way to do that. So instead, the Beck's approach was, instead, well, if you can't split the x-axis, the x-axis is the domain. If you can't split the x-axis, then maybe you can split the codomain. That is the y-axis. Like this one here, this is the domain. So instead, split the y-axis. Right, so this is our codomain. And this works because, so recall, we're looking at x going from omega. You're looking at x going from omega into the positive numbers, right? So we can't split the domain, but we have a positive half line here, and we can split that just as we split the interval 0 to 1 in the Riemann case. Okay, so what you then do is so how do we split that? Instead, split the x-axis. Right? So you pick, so for example, just as with the Riemann integral, you can split the x-axis in many different ways. And it doesn't really matter how we split it. In the end, all these limits over here you're going to get is going to be the same thing. And something similar is true here. You have a lot of flexibility. You can split this interval 0 to 1, and consequently, this is going to lead to a splitting, and consequently, a split of omega. For example, you can split this interval by what? Something like what would be I divided by 2 to the n. So you fix n, and then run these indices. Let's run them up to n. So if I want to n there, I need to run them up to n to the 2 to the nth. So let's look at maybe just a couple of examples. If I look at fix n, you're looking at this is a way of splitting this interval 0 to infinity. So if n is equal to, say, 2, then what am I dealing with? I'm dealing with I divided by 4 from 0 up to what? 2 squared. This is 4 times 2. This is 8. So my chopping of the intervals will be, I'll start my chopping at 0, and then I'll have a quarter, a half, 3/4, 1, and this will go all the way up to the last point, which will be, so 2, this was my 8 in there, this will be 2. And so if I do n equal to 3, my splitting will be I divided by a lot. So what will be 2 to the 3? This will be 2 times 2 is 4 times 2 is 8. And I'll be running 8 times 3, I'm running up to 24. And so now my splitting is going to run again from 0, and then this will be 1/8 now, and then it will be 2/8. This is 1/4. And the end point will go up to 3. So what is happening is that as n gets bigger and bigger and bigger, I'm getting a finer and finer mesh, because you see there's an overlap between the points. I have 0, 1/4, I have 0, 1/4, and now I got 1 point in between here. This is 1/8. And so I get a finer and finer mesh splitting of a bigger and bigger piece. Right. Before I would do it up to 2, then I would do it up to 3, and then for 4 I'll do it up to 4, up to 5, and so on. So as n increases, I get a finer and finer splitting, and the splitting is bigger and bigger and bigger. So then what? If I have such a splitting, then how could I approximate x? So I could approximate x by simple, let me call them xn. Remember, n is the index that controls how fine my splitting is and how long it goes up. So by simple x, what should we put in? By simple xn. So I need to go from x to xn. Okay, so how do I do that? Well, I'll look at my my splitting here. This is going to be up on, this is my y-axis. Here's my y-axis. So let me look at the set of omegas. So I'm splitting the y-axis. I'm looking at the set of omegas for which my random variable that I'm trying to approximate, just as we were trying to approximate this function here by these rectangles. Like this f of x here is going to get approximated by f of x, which is then flat, and then jumps, flat, and then jumps. So we're trying to do something similar here, but instead of splitting the horizontal axis, we're splitting the vertical axis. So how are we going to do it? Well, we'll look at those omegas where x is between, it's in one of these bins here. So let it go between -1 divided by 2 to the n, up to I divided by 2 to the n, and then keep it open. Should we keep it open here or there? Let me do it this way. Right, so this is going to give me a way to split my omega. This here I could call for what could I call it for? A I, and then there's also an independence. Let me put the n up there. And of course, there's also a possibility that x is really large. So I also need to look at this omega, these omegas for which where x of omega is huge. So when it's bigger than the biggest cutoff point, was n. So maybe I should just call this for 8. These sets here, they just joined. So A1, N, A2, N. This runs all the way up to I runs all the way up to N to the 2N. So this is the biggest I that I can have is N to the 2N. And then my last one is my AN, the disjoint. So if I define, so now I take one of the cells to look at the indicator for AIN. I'm going to try to create my simple random variables, the xn's. If I am on the this set here, I know that the x is between these two values. Okay, so I know I'm going to be summing here from I equals 1 all the way up to the n to the 2nth. And I need to put a value here. And if I want to get a lower bound, just as we did, we could have Riemann lower and upper sums. Let's do a lower sum. That means that on that set, I'm going to pick the lowest value for x. And then, of course, there's also the last set I need to keep track of here. I know I'm bigger than n, so if I put an n here, and then the indicator for a. So then, all these x's, they are less than x. They're less than x because on each of these cells, I pick the lower bound. I pick the lower bound here, pick the lower bound here. So I know that they're less than x, and the xn's, the increasing, not only the less than x, the as n increases, I get a bigger and bigger random variable. And this is where we're using the fact that the nest, I get a finer and finer mesh, the nest, this, like the third one is going to contain all the same points as the previous one. So the nest, I'm going to get an increasing sequence. And so what we want, so we want a definition. We want a definition of this expectation of x. We want a definition of this expectation which implies this monotonicity property. Which implies the monotonicity property. And we had already talked about monotonicity properties early on today. We had talked about, let's see if I can find the slide. we had already talked about monotonicity properties. Like we wanted the probability measure to be monotone in the sense that if I were to compute the probability of bigger and bigger sets, I wanted to get this monotonicity property, as one of you said, I want to be able to pull the limit inside. And that's exactly what we want to do. We want to be able to pull the limit inside and then figure out what this limit in here is. And if you have this monotonicity property where stuff gets bigger and bigger and bigger, well, the thing that you get when you pull it inside is going to be the union. Likewise, if you had the another monotonicity property, the decreasing property. So the one that I'm talking about now, it has an increasing property. These xn's that I got myself created, the increasing, the all less than x, the increase, and we want, and not only do the increase, we actually have that if I compute the pointwise limit, so the limit as n goes to infinity of xn of omega, I'm actually going to get x of omega for all omega. So the do increase and the limiting object is going to be exactly this random variable that I had. So we want a definition which preserves this monotonicity property. So what does it mean to preserve it? Well, it means that if I am to compute the limit as n goes to infinity of the expectation of xn, I want this, I know what these are because each of the xn's are simple and elementary, so I know what this here is. What I don't know is what I have here on the right hand side, but I want it to be the case that it preserves the same sort of monotonicity as probability measures. And when I pull the limit inside, I'm going to get exactly that limiting object. So we want a definition that does this. So one could say that I could just define it. I could just define the expectation of x to be this. Okay, that is actually perfectly fine. You can do that. This is not the way that, it's at least not the way that all textbooks do it. I'm not, there's nothing wrong with saying that this is what I mean by this expectation, but the way that the textbook does it, and the way that the most textbooks that I've seen do it, you don't use this as a definition. What they do is they have a slightly different definition. It seems like a slightly different definition, but it's the same. The definition that people give is that the expectation of x is defined as a supremum of expectation of y. So here I have my random variable. This is non-negative and it's measurable. This is defined as the supremum of expectations of random variables that are less than x, which is the case in what we had up here. All these x's, they were less than x. They were all simple. So y is less than x and y is simple. And this is the definition they give. This is the definition of the expectation, is this supremum. Right, so this here is going to be a number. This here is going to be a number. It's going to be a positive number, but it could be infinity. It could be plus infinity. And if you have not seen supremum before, so just a note. So the supremum of a set, supremum of A is in some set capital A. This is a, what is that? This is the, it's a big number. This is a big number, so this is, this number this is a small, this is a smallest big number. This is the smallest big number. So what does it mean to be a big number? It means that the supremum of A in some set A, this is bigger than A for any A in A. Okay, so it's a big number, and it's the smallest, this is the smallest such big number. Right, so it's a big number. Right, so let me just say it's a big number if this holds, and then it's the smallest such big number. Right, so if the supremum is equal to, say, A hat for some A hat in A, we say that the supremum is attained and is equal to the max over A in A. But very often the sup is not attained, like in the Lebesgue integral definition. Right, so the notion of a supremum, if you haven't seen it before, it coincides with the max. But the big difference between a supremum and a maximum is that a supremum may or may not be attained. So maybe just give a silly example for something where it's not attained. What could it be? Something like if I look at the set 1 minus 1 over n. Yeah. When n runs through the natural numbers. So what happens here is that as n gets bigger and bigger and bigger, this 1 over n gets to be smaller and smaller and smaller. So if I try to do the max over n and n of this 1 minus 1 over n, and this is not attained. Right? I cannot find any n that will maximize this. But if I look at the supremum, what's that value? What is the biggest, smallest number here? So I need a big number that is bigger than all of these ones here. And I need the smallest such big number. What is it? Well, I could pick 5. 5 is bigger than 1 minus 1 over n for all n. So is this a good one? Well, let's go check the definition. Is 5 a big number? Is 5 bigger than all of them? Well, no matter what I put in for a natural number here, I'm going to get something that is less than 5. But is it the smallest such big number? Could I find a number that would satisfy this that is smaller than 5? Well, 5 is not going to work. What about 4? How far down can we go? far down can we go, guys? I see chat moving around. I need to get better at this chat thing. How far down can we go? Would 4 be the smallest big number, or can we find something that's even smaller? One. There's a bit. Is it equal to 1? Is it equal to 1? Well, let's have a look. Is it always is 1 minus 1 over n? Is it always, that's the first property, is it always less than 1? And the answer is, well, this is the same as saying that minus 1 over n is always less than 0. And the answer to that question is yes, that works. Now, can we get close to 1? And as you move n to infinity, you get arbitrarily close to 0. So this is good. But as you can see, it is impossible to find any natural number. It's impossible to find any natural number such that when I put that natural number into this difference, I am going to get 1. Sometimes when we talk about supremum and situations like this, it's just quite important to keep in mind that plus infinity does not belong to the natural numbers. It's not possible to take n here to be plus infinity and stick it into this formula, because plus infinity is not here. Of course, plus infinity is also not going to be a real number, but plus infinity is an element in, say, this interval. Right. Plus infinity, it is not a natural number, and it's not a real number. It's also not a complex number. So one can ask, can I always take the supremum? And the answer is yes. So questions like existence and of sup. There's also the other one, inf. The infimum, this is quite similar. If I were to take the infimum over a set A, yeah, what would that be? It would be, this is a small number, right? So the infimum is going to be smaller than A for any A. So it's a small number, and it's the biggest such small number. That's the infimum. And this has to do with R's completeness. Right? Q is not complete. The rationals is not complete. It would take us way too far to start discussing why am I allowed to write supremum up here. If you have taken a course in real analysis, presumably somewhere in that course there would be a discussion of suprema and infima, and why do they exist and when do they not exist. So when you're working with number systems like this one, they do exist. The price you have to pay is you cannot be guaranteed that the supremum here is an element in the same set over which you're taking it. For example, so you can get outside the set. And a silly example is if I do a supremum over n in the natural numbers, and I just take n itself. Like, what is the, so I need a big number that is bigger than all natural numbers, and it's the smallest such big number, right? So all these n's here, they are finite, right? So this is all these expectations here, they are finite, but they could be blowing up to plus infinity. And here's a simple example like that. I can easily get outside the real number system when I take supreme. So this is not an element in the real number system. So this is R's completeness. This is for bounded sequences. So this is R, and you would have to extend the numbers to be including minus infinity and plus infinity if you want to get it in general. And we only deal with negative sequences for now, so we only need the positive part. Okay, so this was a little bit about, I am guessing many of you have seen the super Lec3B before, but this here is the formal definition of the Lebesgue integral. Like, inside here, you have these elementary or simple random variables. You know how to take expectations of them because this is what we've been discussing. And then you get the expectation simply by maximizing over all these expectations where the function is simple and is less than x. And then the big theorem that one that moves on to prove the cornerstone of the theorem. So this is the Lebesgue's monotone convergence theorem. But then you prove this is Lebesgue's monotone convergence theorem. So this is the absolutely the cornerstone of Lebesgue integration. You prove the theorem that says that you have indeed this monotonicity property. So if you have random, you don't have to be simple, but if you have random variables that are monotonically increasing, well then this definition you have up here has the property that when I compute the limit as n goes to infinity of the expectation of xn, the monotonicity allows you to pull this limit inside and you get the limit in here. And this was the property that we wanted. So here, this is just a note. The xn's, that sequence does not have to be simple. And so the reason that we had a discussion about these monotone random variables over here. The reason that people don't use this here as a definition is because here the xn's that we had gotten ourselves created, they were all simple. So the more general theorem is that you can have that property, that monotonicity property, but you can have it for the xn's being non-simple. Like this limit here in that example up here would be exactly x. Right? And these xn's in this example up here, they will all be simple, but for the Lebesgue monotone convergence theorem, we don't need that. So this is the this theorem is, that's the cornerstone. If you were to take a class in measured integration theory, this would be like, I mean, this would be the highlight of the course. This result here is everything that follows related to integration theory. This comes from the monotone convergence theorem. And one should not take it lightly. There really are, I had some examples prepared. Let me just do a few of them. Let's just show you some examples of this. Is not so trivial. If I looked at, let me do omega to be something like an interval 0 to 1. We had that one before. And then I want to look at functions. Say fn of x. How would it be? I would pick them to be n when x is small. So x is small, and then I'll pick them to be 0 when x is big. And so then I could try Lebesgue's monotone convergence theorem here and see what I would get. So if I were to, on one hand, look at the limit from 0 to 1 of fn of x, this would be equal to, it'll be n, right? And then I'll have a 0 when I'm big, and I have a n when I'm small. So this is from 0 to 1 over n, and dx, this is equal to 1. So undoubtedly, if I compute the limit on the left-hand side as n goes to infinity of these integrals, I'll get 1. But if I look at the limit as n goes to infinity of fn of x, and if I pick an x here in my space, 0 to 1, what would this be? Well, what's going to happen is, this is my 1, this is my 0. I pick an x, say I have x sitting here. And then the function is, it starts out being 1 everywhere, right? And then it drops to a half. Let's say that this is a half. And then it goes up to 2. And it goes to 1 over 3, and it jumps up to 3. So when I compute the limit, I fix a point between 0 and 1. I fix a point. The question is, so the first f1 at that point is going to be 1, and then f2 at that point is going to be 2, and then f3 at that point is going to be 0. And then it's going to stay 0 there afterwards. And you can see this is going to be true for all x's. It doesn't matter where I put an x. I can put an x in here. Ultimately, this is going to become 0, and then the spike is going to come to the left of it. So this limit here is equal to 0. And so in particular, if I integrate the limit from 0 to 1, I'm going to integrate to 0, I'm going to get 0. But this is different than 1. Right, so this part here implies that if I integrate the limit of fn of x, I'm going to get 0. Right? So you cannot just say that, well, I'll take the limit of the integrals that's going to be equal to the integral of the limit. And here's an example where that fails. And it fails pretty spectacularly because one of them is 0 and the other one is 1. So that doesn't work. So in other words, the conclusion of the Lebesgue monotone convergence theorem, this is not something one should expect in general. here the assumptions are that you have monotonicity of the functions that you're computing the expectations of. And if you have that, well, then you're safe. You got the limit. You take the limit inside or outside, you're going to get the same value. But if you do not have this monotonicity, or if you don't have something else, it can fail. Have you guys seen examples of when you cannot move the limit inside the integral before? There are lots of examples. We can do another one. If we take one from the homework that you guys did, if I look at the shared screen, I thought I had the homework just here. Gosh, it's a mess. Here's the homework. Here we're looking at this was homework number 2, and we're looking at exponentially distributed random variables. So we have this density here. F of x is this alpha times e to the minus alpha. So if I take, maybe I could take these ones and see if I can create yet another counterexample to this conclusion of the monotone convergence theorem, and let's try to do that. So another example would be if I look at the exponential densities. How would that be? So if I'm exponential, I'm going to be on the I'm going to be positive, and I need my functions. So I'm going to have f of n of x. You're going to be f n of x are going to be these densities that we had before. So I'm going to do 1 over n times e to the minus 1 over n times x. And this here is for x and omega. These were the ones we had in that homework exercise. So the exponential densities, and we know because they are densities, we can integrate them. So now we integrate over the interval 0 to infinity of f n of x. This is going to become a 1. I mean, it is a density, but what doesn't work very well is if I look at the limit as n goes to infinity of f n of x, what do we get here? If I look at the limit of these functions as n goes to infinity, what would I get? What would we get here? And try to think about what happens here when n gets bigger. How big does this term here get? Yeah, so there's a suggestion this is going to be 0, and I agree. This is 0 because the exponential component e to minus something positive, 1 over n times x is positive, right? So e to this thing, this is bounded by 1. So you're going to get that this is bounded by the limit as n goes to infinity of 1 over n, right? And this is equal to 0. So again, we have the same situation that if I'm looking at the integral from 0 to 1 of the limit n goes to infinity of fn of x, this is equal to 0. And of course, if I take the limit of the integrals, I'm going to get a 1. So it fails pretty quickly. Maybe we could have a so there's a question about, would the Lebesgue theorem work for monotonically decreasing functions? Yes, it would. And the way that you get the monotonically decreasing functions is, how would you go from this one to the other one? You put in a minus sign, and put in a minus sign, then this here has a minus sign, right? And there's a minus sign here. The limit, if you can move a minus sign inside a limit, that's going to be okay. So yeah, it would work for monotonically decreasing functions too. But then you would have to be, then you would be, it would be negative. But there, yeah. So if you have a sequence of monotonically decreasing functions, if you can change the sign on them so they become positive and monotonically increasing, then you're good. Then you can use this theorem, and then you get, it'll be minus sign here, you pull the minus sign outside, pull the minus sign out here, and you're going to do the same thing over here, cancel the minus signs out, and you're going to get that it works for such monotonically decreasing sequences. I'm not talking here about complete general monotone sequences, because here I'm requiring positivity. I'm requiring positivity. I haven't said yet anything about what happens if I have random variables that can be both positive and negative. Right? And we know that's going to be trouble. We know it's going to be trouble because of that homework exercise you had with sine x over x. Right? There's something there about that is going to lead to trouble, because if I take absolute values there, I'm going to integrate to plus infinity. So I don't think today we have time to discuss that further. What I have in mind is to look at a few more examples, and then call it quits. Yeah, but you can get Lebesgue's monotone convergence theorem to work for decreasing functions too. Just make sure that when you do, you transform with this negative sign, and that the resulting sequence of functions has to satisfy the properties that you have here. A more constructive, or maybe a positive result related to Lebesgue's monotone convergence theorem would be, if I look at the case where my random variable, my x, it goes from omega, but instead of going into R, it takes on fewer values. So it takes on like x1, x2, it takes on these ones, and this is countable. Then how would we compute the expectation? How would we compute the expectation? We would say, well, we'll do maybe AK. We're going to do the splitting of omega, right? So we're splitting now. The y-axis is going to be these points I have in here. I'm going to be splitting now according to these various points. So I will look at those omegas such that x at that omega is going to be xk. Right, so remember this here, this is shorthand notation for those omegas such that x of that omega is exactly xk. These ones here are just constants. And then we can see and these are disjoints, right? Here, disjoint. There's no way that x can take two values simultaneously, because then it wouldn't be a function. So these are disjoint sets. And I can, for example, write x. This would be nothing else than if I'm summing over k from 1 to infinity of this xk, and then the indicator for ak. So I have the assumption I'm working on now is that my random variable takes on values in this countable set here. It's I can now make a disjoint splitting of omega. So if I have my omega here, I'm going to split it up in these cells where x takes the value of xk on a given cell. So this is a partition of omega. So you're not only disjoint sets, this is a partition. Right, so that means that the union of all these sets, this is exactly going to be omega. Okay, so now I can use the monotone convergence theorem to calculate the expectation. How would I do it? Well, I would we would use that when I'm looking at so now we note that if I'm summing from 1 to n of these xk's, this is less than if I'm summing up to n plus 1 of these xk's. Like, is this clear? Well, yeah, it is, because this is an equivalent claim to saying that if I split out the sum here, I'll get the first term. This is going to be less than, that's the claim. So this is going to be the same as simply just splitting up to the first n, and then add on the last one, which is number n plus 1. Right, so this is the same. I subtract away on both sides. This is the same as saying that this thing here should be positive. But that's true, and this is true because my x, this is true because my x's here, they were positive. Right, so I have monotonicity. And furthermore, I also have that when I pass into infinity, I'm going to get exactly x. Right, so the monotone convergence theorem it gives us that if I take the limit as n goes to infinity of the left-hand side, I'm going to get the same thing as when I pull the limit inside. So that's monotone convergence theorem. It gives us this one. Now this limit here, this is going to be exactly the expectation of x. This is when n goes to infinity. This sum here becomes the sum from k equal 1 to infinity. That's my x. And now on the left-hand side, what do we have here? Well, we can pull the sum out, we pull the constants out. So on the left-hand side, we're going to have the limit as n goes to infinity. We're going to have the sum of xk, and then we're going to have the probability of ak. And we can write this here as the sum from k equal to 1 to infinity, xk times the probability. What was ak? Ak was exactly the set where x is xk. So here you see the formula. What is the expectation of a random variable when the random variable takes values in a countable set? Well, that expectation is the probability of it taking a given value times that given value, and then you sum them up. But so this is quite similar. This is a more general case. A special case is what we had in the binomial model. This is a special case of our binomial model. Right? Remember, we had an expectation of a random variable. What did we call it? Say x. This would be p tilde, and then I would have x evaluated at what? X could be, there would be two possibilities. Either you would have tails or you would have heads. So p tilde was heads plus q tilde of x of tails. Okay, so we split up this probability here. This was exactly, this was the probability under the tilde measure of where that random variable psi would be u, and this would be where psi would be d. So here's a more general formula. Instead of just having two values, this thing here now allows us to take countably many values. Any questions on this one? We've got a few examples now, and we derived this this formula, which is a generalization of what we've seen in the binomial model. It's also a generalization of this property that we had with the probability measure, namely that the probability of a disjoint set, the probability of a collection of a disjoint union, probability of a disjoint union would be the sum of the individual probabilities. So here we're allowing to scale that. If, for example, yeah, so this one here is more general than the measure property we have, where P of a disjoint union would be equal to the sum of the individual P's on these sets in that disjoint union. The last thing that maybe we should do today before we call it quits is just want to make a comment about this one here. Right, so we're dealing with functions that are finitely valued, but when we start integrating them, they could become plus infinity. So you have seen that in the homework. You have seen versions of this in the homework. Like, so not all integrals, so not all expectations, are finite. So if you look at your homework, you would have integrals from 0 to 1 of this x to the alpha dx. This could be, this was in homework 1, right? This could be, this thing here belongs to 0 to infinity, right? This is an element in here, and this you could have. It could be plus infinity, right? You saw examples of alpha here. If alpha is sufficiently small, if it's very negative, like if it's -2, like an integral from 0 to 1 of 1 over x squared, this is going to become plus infinity. Right? Even though 1 over x squared, this is finite for all x. Right, so you're taking a function which is finite, and you can integrate it, and it can blow up to plus infinity. So this is a situation that I'm allowing for here too. Right? You have a function, you have a measurable random, you have a measurable function, a random variable which is finite, but when you integrate it, it could blow up. And so here was one example in your homework, and let me just show you another one in our so a similar example. Can be given in the multi-period binomial model. And so let me try to do that. So we're going to be looking at an infinite number. So this is countable of coin flips. Right, so what I'm looking at, so omega in omega is a vector. It's a vector, so omega is equal to omega 1, omega 2, omega 3, with omega n either being heads or tails. So first question, is omega countable? This is where it starts to get tricky. Is omega countable? So I'm looking at vectors that are strings of numbers, heads, tails, heads, tails, heads, tails. Right? So you can have, so examples of such omegas would be, omega could be heads, heads, tails, tails, heads, tails, and so on. That's a long infinite string. And then I'm taking all these points, all these possible strings. Then what? Is it countable? So Jose, he's saying, isn't this the real set? And that's not countable. This is no. Jose, do we have a, I apologize if I'm butchering your pronunciation, but Jose, do we have can you give an argument for why this is? So you're right. Can you give an argument for why this is not countable? Or anybody else, it doesn't have to be, it's open. Can we, why is this not countable? Or why not?
If there's like an infinite number of coin flips,
Yeah. Yeah, so how many different coin flips combinations can you come up with? Is it countable or is it not?
I think there's so many, so it probably might not be countable.
Yeah. Yeah. So what? Maybe if you were a computer scientist, the computer science folks, including my wife, they like these heads and tails not to be heads and tails, but they like heads to be 1 and they like tails to be 0. So then what we're looking at vectors we're looking at vectors that are infinitely long and you have zeros and ones on them. Can I write any real number, say between 0 and 1, in terms of zeros and ones? Yeah, I can, right? If I pick a number between 0 and 1, can I write x? Can I write x as 0 dot omega 1, omega 2, omega 3 with omega k being 0 and 1? Is that possible? That's possible, right? Because this is just a binomial expansion. So this one here, would count the halves. This one here would count the quarters. This one here would count the eighths. This one here would count the 16th, and so on. And Pusher says that this is actually true. He did it in his own class, and this is true. This here is a world-famous argument due to Cantor. This is Cantor's diagonalization argument. And so in math, there are lots of cool things, and this here is one of them. This is a super cool trick. What Cantor he does here is an extremely simple argument for why it has to be like this. He argues that imagine that this really was countable. Imagine that it really was countable. Imagine omega was countable. Then he says, so you're going to write x1. You're going to write x1 as 0 dot omega 1, 1, omega 1, 2, omega 1, 3, omega 1, 4, and so on. And you're going to write x2. You're going to write this big sequence. It's going to be 0 dot omega 2, 1, omega 2, 2, omega 2, 3, and so on. And it's going to go down to xn. It's going to be 0 dot omega n1, omega n2, omega n3. And he's going to keep doing that. This is, if it was countable, I could list my elements in this crazy fashion, right? And then he says, okay, so let me create a new one. Create a new x, not on the list. And the way that Cantor, this is why it's called the diagonalization argument. He says, well, this omega 1, 1, this is either gonna be 0 or it's gonna be 1. And he says, if it's 0, you flip it to be 1. If it's a 1, you flip it to be 0. So you flip it. Flip from either 0 to 1 or 1 to 0. And you do that thing to that one, you do it to that one, and over here you're going to have n, you're going to flip that one. So now on this string here, on this diagonal piece, everything has been flipped. And that's going to be your new x. This diagonal structure here, this is going to be your new x. This is how he defines his new x. And this new x is going to be none of these x's that you have on the list, because it's going to differ at least in one spot from every single element in the list. And that means that this is impossible, because it should have included this x, so you're not countable. So the infinite conflict space is not countable. So let me just show you an example of this this phenomenon that's going to happen on this infinite space of a random variable which is finite, but when you compute the expectation, it blows up, and then I think we're going to call it quits. So on this on omega, we define a random variable x. It's going to be a random variable x. It's finitely valued, but when I compute the expectation, it blows up to plus infinity. The textbook calls this one here a St. Petersburg paradox. I think he spells it with a K. So here's the way to do it. So I'm going to attempt to create the sample space, even though it's an infinite string. I'm still going to attempt it. So the first one is heads. Up in this top part of the tree, if you get a heads, up in this part of the tree, my random variable x is going to be 2. Then if I get a tail, so the first one is heads, I get 2. Okay. So if the first one is tails, then two things can happen. I can move up, and then I'm up in this part of the tree. So here x is equal to 2, here x is equal to 4. And then I can go down the tree. So a double, I can get a heads. I can get a heads. If I'm heads, so if I'm tail, tail, and then heads, I'm going to get an 8. And then I'm down here, so I get tails, tails, tails. Well, then I'll do the same thing. I'm going to get 16, and I'll continue down, so on. And just for completion, if my omega is equal to all tails, we set x of omega just to be 0. But this here is a finally valued random variable, right? It goes from 2, 4, 8, 16, 32, and so on. But if I compute the expectation, what is it going to be? Well, I use this formula that we derived, that I can break it into these disjoint sets. So, okay, when do I get 2? I get 2 if the first one is heads. So let's do a fair point. Fair points. So P is a half, and Q is a half. So I do the expectation. So what is the probability of x being 2? Well, x is 2 exactly when the first one is heads. Okay, so that's going to give me the probability half times 2. Okay, there's more in the set. I go down 1. Okay, so when is x equal to 4? Well, x is equal to 4 if the first one is tails and then the second one is heads. Okay, so the independent, fair, and independent. So that's going to be half times half, this is a quarter, times the value, which is 4. Okay, so when is x equal to 8? I need tails, tails, heads. And what's the probability of that? It's a half times a half times a half. That's 1 over 8 times the value of 8, and so on. And so you see what you end up with here is 1 plus 1 plus 1, and this is equal to plus infinity. So it's an example of a model that has a random variable, and the random variable is finite, but the expectation is plus infinity. Okay. Are there any questions or comments at this point? Any questions or comments at this point? Otherwise, I think this is a good place to stop. So just to give you an idea about where we are in the process. So we've been able to define now what the expectation is. Let me find the sheet. We've been able to find the expectation. Can't find a sheet of paper. We've been able to define the expectation. We looked at some examples. We talked a little bit about monotone convergence. The next big ticket item is to define these conditional expectations. And as soon as you can get these conditional expectations defined, it will allow us to introduce martingales. Conditional expectations, this is the tool that will lead to martingales. Right? And martingales, this is what we use in quantitative finance. So as soon as you have that, we can move back into the multi-period phenomenon. So this is coming next Tuesday. I just want to remind everybody that we have office hours on Thursday morning and Friday morning with me. And then you have a problem session tomorrow morning with Chow. And Chow also has office hours on Friday mornings. Okay, so please try to take advantage of it. When you get the homework back, if there are problems that you need to resubmit because you have not been, there are two big holes in them, use these office hours to try to get some help to make sure that you get these holes repaired before the exam. Okay. If there are no more questions or comments, I wish you all well, and I'll see you, if not before, I'll see you next week.